Hey everyone, welcome to our sort of first big exploration of aromaticity, and we'll talk a little bit today to get started about what's going on with benzene and why benzene is so special. I've been telling you this for weeks now, that benzene is different, benzene is special. We don't necessarily want to do the same reactions on benzene that we do on other alkenes. So why the heck is it special? How do we know that it's special? Well, we can tell that it's special because we're going to measure its energy in different reactions. And so, what does that tell us? Well, it's going to tell us how stable it is. The other thing that we're going to do when we think about benzene and reactions is that we're going to compare the compound benzene to other similar compounds to get an idea of what their energy is and see if it makes sense that benzene has the energy that it does. And we'll look at an example of this here in a moment on the next slide. The example we're going to be looking at is a reaction that takes place with double bonds or alkenes. And it's going to help us determine what effect the number of double bonds has as a stabilizing effect on benzene. So that statement itself might not make a whole lot of sense. Let's get right into the example so that it will help explain what we're talking about here. This is an energy diagram that's going to allow us to compare some different molecules together to see what their energy levels are in this hydrogenation reaction. So you don't need to know anything about the chemistry of this hydrogenation reaction. For our purposes to help explain what's going on here, you should know that we take an alkene or multiple alkenes. We're going to use hydrogen gas here in the presence of a catalyst, and that's going to basically stick those hydrogen atoms onto our molecule that we started with, and that's going to turn it into an alkane. It's going to take the double bond, kind of get rid of it, and give us an alkane at the end. But the other important byproduct is heat. And so by measuring the heat that's coming out of these reactions, we can tell how much energy is released when we perform this reaction. And since the only thing that's happening in this reaction is getting rid of those double bonds, it tells us how much energy is kind of inherently stored in those double bonds. So if we look at what we've got here to start, we have two compounds that we're going to compare to one another, and we'll add a few more in as we go along here. So what's happening is that we're just taking these molecules here. So this is cyclohexene because it has an alkene in there. And then here is a dialkene with the same 6-carbon ring, right? But now it has 2 alkenes in it instead of just 1. So what we're doing here is we're taking each of these ring compounds, adding hydrogen as necessary, and it's releasing some energy. And at the end of the reaction, both of these compounds are going to end up here, and that is a molecule that we call cyclohexane, right? We are used to seeing this in plenty of our practice problems. So that's kind of like the cyclohexane here is our energy baseline. We're calling that kind of the 0 on this diagram. And everything else is going to be higher in energy than that based on the number of alkenes it has, right? So if we are to take this first one, cyclohexene, and we add 1 equivalent of hydrogen to it in the presence of this catalyst, we get out an amount of heat that works out to 120 kilojoules per mole. Don't worry about the kcals per mole. And in general, you don't actually have to worry about these numbers as far as knowing them for the long term. Just hang on to them in your brain while we're on this slide to help you understand where these differences in energy come from. But you don't need to memorize these numbers. Definitely don't worry about that. So this kind of tells us that if we have 1 alkene inside of a 6-membered ring, that is worth 120 kilojoules per mole of energy. That's our assumption, okay? So if we go to this next one, and like I said earlier, we add some hydrogen to both of these alkenes, we end up measuring an amount of heat that's released, which is 231 kilojoules per mole. So if you're doing a little bit of quick math in your head, you'll say, that's not quite double what we got before, but it is pretty close, right? If we were following along in a perfect mathematical world, right, 2 times an alkene should be exactly 240 kilojoules per mole. So we're at 231. It's a little bit low, but it's pretty close. The other thing that you could maybe say if you're thinking critically about what we're starting to learn about for this portion of the unit is that because these double bonds are next to each other, right, they form the correct pattern or motif to allow them to resonate with one another. And so that could be a little bit of a stabilizing factor that means that this energy is a little bit lower than you might have already thought. So that's kind of our baseline, right? And then we have to bring in the concept of our benzene, right? But we can't exactly bring it in as it is because we know there's something kind of funky and special about benzene. So what we have to do instead is bring in this sort of fake hypothetical molecule that we're calling cyclohexatriene. And it's not benzene, right? The reason that this is drawn so funny, I mean, look at these angles, like what's going on here? Why does that look so bad? It's drawn on purpose, distorted, to show that their bonds are farther apart, which means they don't have the ability to resonate to one another. That's what we're trying to do, is trying to keep them in a ring, but like keep them sort of saved away from each other and isolated, right? So this is totally isolated, no ability to resonate, cyclohexatriene. This is what we would expect benzene's energy to look like. We would say it is 3 times 120 kilojoules per mole, or 360 kilojoules per mole. So this is kind of our theoretical value of energy. That's what benzene should be. But what happens in reality when we measure the value of energy of benzene for this reaction is that it's much lower, right? It's actually even lower than just having 2 double bonds. So this platform here is the one that we're looking at for the energy of benzene. It's only 208 kilojoules per mole. So it's not like 1 double bond, it's not like 2, and it's definitely not like what we would expect to see for 3 double bonds. And so when chemists were first sort of trying to figure out what was going on with benzene, when they noticed this difference in energy, they said, yeah, that doesn't really make sense. And so they were beginning to call it something along the lines of resonance energy, because they were aware that the double bonds could interact with one another in a resonance type of fashion. So there is this sort of difference in value, right? That's 152 kilojoules per mole, that it seems kind of out of place, right? It should be much higher. This as an amount of energy that is ascribed to the stability that we gain from, instead of having this theoretical, totally isolated system where none of these alkenes can talk to each other. If they can talk to each other, it saves us 150 kilojoules per mole of stabilization energy. So this is where we got the basis of understanding, hey, there's something definitely different and kind of special about benzene and some of the compounds that are related to it in structure. So one of the originators of the idea of this class of molecules decided to dub them aromatic, or aromaticity, as the concept for what binds these types of compounds together, what makes them special. And it may be the case that it was so called because benzene and some of its derivatives have a really pleasant aroma. But in actual fact, this is probably a bit of a misnomer, because a lot of the molecules that fit under the category of aromatic or having aromaticity don't really have a smell at all. Some of them do. Some of the compounds that I've worked with in the past smell like, just a beautiful floral smell. I had one that smelled exactly like maraschino cherries. So they can have a lot of smells, but they don't necessarily have to. And there are plenty of molecules that have smells that are not aromatic. So when we talk about aromaticity, whether or not they actually possess any kind of a detectable smell, they all do have something else in common. They all have to have a cyclic cloud of electron density. And this cyclic cloud of electron density is present both above and below the sigma bonds of our molecule. So what does that look like? Let's take a peek at this sort of diagram. This is just from the Wikipedia on aromaticity. We can see our kind of regular Lewis structures style drawing of benzene. These are called Kekulé structures for August Kekulé, who is a German chemist who first proposed the idea of these being interchangeable forms of benzene. They're truly just resonance forms of one another, but you may see that word written out somewhere in his honor. But what we're really looking at as far as an orbital picture is like these 2 pictures at the bottom here. When we look at each individual carbon atom on our benzene ring, we can see that at each position, they all have these p orbitals and they're sort of overlapping one another. So it can be a little bit hard to see, but I can kind of trace one of them out for you like so. And because they're all quite close to one another, and because they all are, standing up kind of like, bowling alley pins, right? They're all aligned perfectly. They can overlap just like we did in regular alkene bonds. But since they're all right there, they can all overlap. And what that ends up giving us in more of a molecular orbital picture, so not just looking at individual p orbitals, looking at the whole molecule itself, it gives us this kind of donut shape of electron density. This one up here is above, and this other one is sort of supposed to be below here. And then that drawn in single bonding framework represents those sigma bonds that are keeping the carbons bonded to the hydrogens and the carbons singly bonded to one another, right? So this cyclic cloud of electron density, the fact that it can go all the way around in a circle is the thing that's really powerful. Because if you were to do our hydrogenation energy experiment for linear compounds, then they're not going to show the same pattern of dipping down when you get to 3 double bonds. Benzene, being in that ring shape, is really special. So in order to be in this kind of special club of aromatic compounds, you have to follow a set of rules. Or else. Now, what do I mean by that? Now, we'll come to that in a moment. Let's talk about the rules first. There are 3 major rules for aromaticity, and you absolutely have to follow these or you don't get to be in the aromatic club. So the first thing is that the compound itself must be completely a ring. Now you can have stuff sticking off of the ring, but it has to have a ring shape to it. And then we'll see, we have some more caveats about the ring itself, but it has to be a ring. You might also hear me call this a cyclic molecule, meaning cycle, meaning round, meaning going around, meaning a circle. So the other thing that we have to have on every single carbon or other atom in the ring, because we can have oxygen, we can have nitrogen, we can have some other atoms, all of the atoms inside of the ring must have available p orbitals. And maybe it's clear already to you why we need that. If we go back to this picture, we have to have p orbitals at every position, otherwise we can't make a full ring, right? So that's very important. And our p orbitals can look like a few different things, right? So in the case of benzene, and I want to say normally, you're going to have a lot of double bonds there, because we know those are made up of p orbitals, but you will also start to see positive charges, right? So we talked about those in the resonance video about how they are an empty p orbital, so they're there, they're available. And even a negative charge pair of electrons can be in a p orbital. Typically we think about those as being in a hybridized orbital, but what we'll see is that they're allowed to kind of change their hybridization a little bit in order to achieve aromaticity. So that can be a lot of different things, but what you want to be looking out for is if you have an sp3 hybridized carbon. Those are bad. Those are resonance roadblocks. They're aromatic roadblocks too, and they're not what we want to see here. And last but not least, each of these molecules must be fully planar. Why does that matter? Well, again, if we look back at benzene, it's a kind of a small ring, so it just sort of seems like that's the best way to have 6 carbons arranged is totally flat. When you get to have more and more carbons, they don't want to be flat as much anymore. And so that can be a little bit of a problem, because if they don't sit and lay flat like this, then their p orbitals won't be aligned correctly. And then we can't have our resonance and we can't have our little donut of electron density. So we have to have planarity to all of our compounds. And you might say, well, Grace, how am I going to know that? It's pretty easy. If you have 8 carbons or more in your ring, it's not going to be planar. If you have 7 or less, you're good. It's totally planar. You don't even have to think about it. Okay, so those are our 3 rules for aromaticity. And if we don't follow these rules, then, well, like I said, we're not in the club. And if you're not in the club, you are non-aromatic, right? It just means that you're a molecule, but you don't have aromaticity, you're non-aromatic. And so that is a possibility that we have when we're looking at compounds. You can say, yeah, that's not aromatic. And we'll see some examples of that coming up shortly. But we have aromaticity that we do need to think about quickly. And there are two categories of aromaticity. So that's kind of interesting, right? This is where that follow the rules or else comes in, because there's kind of a fourth rule. And that fourth rule is based on the number of electrons that you have in your pi system. Right, so that's the number of double bonds. It's if you have a lone pair of electrons, we have to count all of those up. If you have an odd number of pairs of electrons, then yeah, hey, you are cool, you are in the club, you are aromatic. And that's what we want. That's nice. We like that. That's stable. That's happy. And our example for that is, of course, going to be benzene. It's the poster child for organic chemistry and definitely for aromaticity. If we think about how many pi electrons there are here, we have 1, 2, 3 double bonds. Each one of those is a pair of electrons. So that's 3 pairs. You may see in other places a rule about how many single electrons there are. So you may see 6 electrons. That is the same thing as 3 pairs. I think it's easier to count in pairs, but choose whichever method works for you. If we have an odd number of pairs, we're good, we're happy, we're aromatic. But if you don't obey the rule of having an odd number of pairs and you have an even number of pairs, but you fit all the rest of these criteria, you're still aromatic, but not exactly. You have to be anti-aromatic. So what is that about? Well, we didn't talk about it at the top of the lecture today with regard to energy and stabilization, but if you have this anti-aromatic nature or anti-aromaticity, that's bad. That's unstable. We don't like that. That means that you are actually way higher in energy than you should be. So I will also say maybe they're evil. There's no evidence to substantiate that. Unless, no, only joking. The reason that these are so unstable and kind of bad, and definitely not evil, but they just literally don't stick around. They're so unstable, they don't stick around enough for us to really do a lot with them. You can make them and study them, but they're not stable. You can't put them in a bottle and leave them on a shelf. You make them, you can study them, and then they're going to react and form something else because they're so unhappy being anti-aromatic. So you have to have an even number of electron pairs to be an anti-aromatic compound. So here's a kind of a funny looking one. If we have a 4-membered ring, right, a little square that has 2 double bonds in it, and we count that up, it's 1, 2 pairs. So that is our anti-aromatic, our nemesis of aromaticity, that is not so great and doesn't like to be anti-aromatic. In fact, they will do some funny contortions to try to avoid being anti-aromatic, but we won't have the time to get into that this semester. What you will need to be concerned with this course is being able to tell the difference between something that is not aromatic, anti-aromatic, and aromatic. So let's do some practice with that, shall we? So here is, you'll see me call this A, AA, and NA for aromatic, anti-aromatic, and non-aromatic. So what you're going to do is sort the following molecules into these 3 categories: aromatic, anti-aromatic, and non-aromatic. So I'm going to draw out some category labels here on the screen for us, and then we'll go one by one through and decide whether we think each of these molecules is aromatic, anti-aromatic, or non-aromatic. So what I recommend you do right now is go ahead and draw out those categories for yourself on your paper. Pause the video, make a solid guess for all 6 of these, and then we'll talk through them together. So here we go. So what I'm going to do first is just kind of move these a little bit around just so they don't look like they're in any of these categories yet, because we haven't decided. So what we'll do is analyze one of them first, go through all 3 rules, make our decision, and then we'll scoot it around to the category that it needs to go into. So let's take a look at this one first. So the first category that I want to go through is the planarity category, because that's going to be an easy one that we can do for all of these at once. I said if you have 8 or more carbons, you're not going to be planar, and therefore you will be non-aromatic. But all of these are under 8, although let's see, what's this one? 1, 2, 3, 4, 5, 6, 7. So this one only has 7 in it, so that's good. That means that we don't have any that are 8 or more, so planarity, we're fine for all of these. We can just go ahead and kind of not think about that one. Let's start with this nitrogen containing one right here. So what are our criteria? Let's think back. First things first, it must be a ring shape. And so this is that. And I would say that's true for all of the rest of them on this page as well. So we can kind of leave that one by the side, but it will be a thing that you'll have to double check on for your homework. Make sure that they're in a ring. Second question is, do all of our atoms in this ring have p orbitals to them? The other way that you can check yourself on that is that, are they sp2 or do they have a lone pair of electrons on them? So for this one, I don't think it's too bad to see that it looks a lot like benzene, right? So this is sp2 right here because it's on an alkene. Same with this one as well. What about that nitrogen? What's the hybridization of this nitrogen? And let's not forget that Grace didn't draw in the lone pair there, but it does have a lone pair of electrons. If we remember back to hybridization, it has to have 3 things around it to be sp2, right? And so that's the case for all of these carbons because they have 2 bonds to the ring and a hydrogen. And then that's sort of similar for nitrogen, has 2 bonds to the ring. And the third thing is that pair of electrons. So this one is also sp2. We're happy with that. Same thing with these other ones around the ring because they all have double bonds to them. Okay, so this has all sp2 atoms. That's good. And we already decided it's planar. So this is an aromatic compound. We just have to decide if it's aromatic, or if it's anti-aromatic. So that means that we need to count up the number of electrons that are in the pi system. So we can do that by counting up our number of pi bonds in the ring here. So there's 1, 2, 3. So that seems pretty good. That looks, again, a lot like benzene, but we need to be careful and ask ourselves one other question. And that's about this lone pair, right? If we need to, sometimes lone pairs can be included in the count of our aromaticity. So you see a couple of examples that have lone pair electrons over here. So are we going to include these ones? How do we know which ones we can include? Well, the thing here is that we don't need to include these ones because there's already a set of electrons coming from this double bond right here, right? That's part of the pi system. If we think about the geometry of this nitrogen, so this is a bit of a throwback to some Gen Chem stuff in the beginning of our unit. These electrons, like we said, are a part of that sp2 hybridized atom, but they're in sp2 hybridized orbitals, right? And so what that means is that it's a part of that planar framework that is a sigma bonding framework, right? So it's not a sigma bond, but it's in the same plane as all the rest of the sigma bonds in this ring. And the sigma bonds are perpendicular to our pi system. So that means that we are not allowed to use those in resonance. If this is a little bit tough to visualize, you can look in your textbook or go online and Google like a model of pyridine. That's the name of this compound. You'll be able to see that that lone pair of electrons is sticking out in the plane of the ring, but it cannot overlap with our pi system, so we do not need to count it into our count of pi electrons. So if that's the case, then we know we have 1, 2, 3, an odd number of pairs of electrons, and that makes this which? Aromatic, anti-aromatic, or non-aromatic? Answer the video question now. That's right, it is aromatic. So it was pretty close to the right position on the page anyway. So there's our first molecule, and that happens to have the name pyridine. You won't need to know the name for all of these, but I'll give you some just for fun. All right, let's move on to this next one over here. It's got kind of a big ring with, this has more stuff kind of hanging off of it than we've seen in the other ones so far. So what's going on here? Let's go ahead and go through our list of criteria and see what we've got. We've already said these are all planar, so that's taken care of. Is it a ring? Well, yeah, there's some stuff, like I said, hanging off of the ring, but for this part of the molecule, right, that bit is a ring. So if we just consider what's going on inside of that, then we can decide whether that part is aromatic. And if that part is aromatic, then the whole molecule is aromatic. So yes, we have a ring. Now, does every carbon in this ring have a p orbital? Let's take a look. We've got a double bond here and here, like we did in the previous example. That's good. This one is a little bit different because it's attached to that O outside of the ring, but there is a p orbital there. So yeah, we're good because it's sp2 hybridized. What about here? What's the hybridization at that carbon? Hopefully you can still remember our hybridizations. That is an sp3 hybridized carbon, as is this one and that one. So really only half of this ring fits the criteria of having an available p orbital. So gosh, we didn't even fit all three of those rules. So this one has to go into the non-aromatic category. It's just not aromatic. Too bad. Not in the club. That's okay. The funny thing about this is a molecule called carvone, which is actually a very smelly aroma forward molecule. Carvone is something that is present in both spearmint and caraway seeds. And if you've had like a rye bread, that's got usually some caraway seeds in it. So it's kind of a bready taste and smell, right? So funnily enough, it's an aromatic molecule that's not aromatic. Anyway, the structure itself doesn't possess aromaticity. Let's move on to another one. We'll do this one over here. Kind of move that over. Okay, let's see what we've got here. We definitely have a ring. That looks good. It's going around in a circle. We already decided that this is planar, so we're set. Now we just have to check for all p orbitals, and it's looking pretty good so far. We've got a double bond here and there, here to there. And then what about this position here? We've got a lone pair of electrons with a negative charge on it. So that is not technically sp2 hybridized, but the availability for this lone pair to kind of conform itself as needed to be able to resonate means that that part is good. We are allowed to sort of what we call rehybridize that and allow it to be in a p orbital if we need it to be. But what about this last carbon? Uh-oh. Wah, wah. It's an sp3 carbon. So it still won't work even with our converting that lone pair over to be in a p orbital. This one is still an sp3 hybridized carbon. So this will not work. We're going to have this be over here in the non-aromatic club. Okay, halfway done. Let's try these other three. So what about this one here? Now we have a 5-membered ring with a couple of double bonds and a positive charge. So again, it is a ring. That's all good there. It has planarity to it. We've decided that it's a pretty small ring, so there's only so many ways you can arrange 5 carbons, and they will definitely want to be planar. Here we have a couple of double bonds, right? Here, here. So those are all sp2 hybridized carbons. That's good. What about this carbocation? Answer the video question, what's the hybridization of a carbocation? Hopefully this rings a bell from the previous unit. Our carbocation is flat and therefore sp2 hybridized. Good. So we fit all the characteristics needed for aromaticity here. And now we just need to count up the number of pi electrons to see which club we're in. If we count up our number of double bonds, we have 1, 2 here. And then what about that positive charge? Well, if it's positively charged, it can't have any electrons to it, so it contributes 0 pi electrons. It's just an empty orbital that will allow other electrons to fill it in. But if that leaves us with only 2, or an even number of pairs of electrons, well, then that's one of our nemesis. That is an anti-aromatic molecule that we don't really like. It's not very stable. Ugh. Okay, let's try this big one down here. Let's see, we've got a ring, goes all the way around like so. That's good. And we've decided that if it's 7 carbons, it's getting close, but it is still planar, no problem. So that's all good. Now we just have to check for p orbitals. Looks like we've got a lot of double bonds here, so this should be pretty easy. All those double bonds have available p orbitals. What about our negative charge here? So this is going to be the same idea as what we had over here. We were willing to say, yep, that one could be rehybridized, quote unquote, rehybridized to sp2 if we needed it to be. And that looks like the case here too. If we allow that one to rehybridize and set that negative charge into a p orbital, then we can call that carbon sp2 hybridized, and then we have full sp2 orbitals going all the way around that ring. So now let's count up our electrons in our pi system here. Here's 1, 2, 3 bonds. That's looking pretty good so far. But now is the question, do we count this one? Yeah, we have to. We decided that we wanted to rehybridize this lone pair into a p orbital so that we could go all the way around the ring. And so that means we do have to count those two as a single pair, right? So that is pair number 4. And that means we have another even number of pairs. So, guess that one's one of our nemeses as well. And last but not least, let's take a look at this one. So this looks very similar to this other positively charged version that we saw before, but now it's negatively charged. Maybe that makes you think a little bit of something about what the outcome of this is going to be. But let's go through the process again. Do we have a ring structure? Yes, it goes all the way around in a ring. Do we have planarity? Yep, we decided that for all of these already. Now we just need to think, do we have all p orbitals here? And again, lots of double bonds. So that one is good. And then what about this last carbon? Same idea here as the previous couple that we looked at. With a negative charge there, we're allowed to decide whether or not it wants to rehybridize. And if we did, similar to the previous example, yep, we would have p orbitals going all the way around the ring. So in that case, we do want to rehybridize that to an sp2 type of carbon. So this molecule fits all the criteria for aromaticity, and then we just need to decide which club it's in. Let's count up our pairs of electrons here. We have 1, 2 double bonds. And then again, do we need to count this one? Yes, if we rehybridize an orbital with a negative charge in it, we have to count those electrons toward our aromaticity. So that is our third pair, and that gives us an odd number of electrons. So that is which? Answer the video question: aromatic, antiaromatic, or non-aromatic. Hopefully, based on the odd number of pairs of electrons, I've correctly identified that as aromatic. Or maybe you could just tell based on the fact that I wanted 2 of each to fit this slide nicely. So anyway, there we go. This is what you definitely would be asked to do on your homework and probably on the exams: identify whether a compound is aromatic, antiaromatic, or non-aromatic. So be ready to practice these skills because you will definitely need them going on through the unit. So with that, I want to talk a little bit about the idea of resonance and how that ties into aromaticity, because we haven't really talked about it yet other than the Kekule structures from earlier. We did this little revisit to resonance in the previous lecture video because I said it would tie into this, and it does. But if we look at this molecule, the last one that we did there on the previous slide, it's aromatic just like benzene is, but it looks pretty different, right, from benzene. Because of that weird lone pair and negative charge there, it's not quite really so symmetric and nice and even looking as benzene. So how is it that it possibly can achieve a nice even ring of electron density? The answer, as you may have guessed, is resonance. So if we are to take this molecule, I'm just going to copy this down here and draw some resonance structures of it. I hope I can convince you that even though this doesn't look super nice and symmetric, it actually is. And this will be a good chance for you to practice drawing your resonance structures too. If you would like to, pause the video now and see how many resonance structures you can draw of this molecule. For the sake of this practice example, I'd recommend numbering your carbons in this molecule so that you can see at which point you have a negative charge sitting on which carbons. So we can go through that here as well. Let's go ahead and put some numbers on. To begin with, I'm going to put them kind of inside the ring here. So we'll draw the electron movement on the outside. So we start off with our compound here that has the negative charge at carbon 1. And what I'm going to do is I'm going to go ahead and pre-duplicate this molecule, but I'm going to erase all of the pi bonds, so just so that we have this ring available to us. Now, let's draw some resonance arrows to show how the electrons can move around this ring. So you can start anywhere with resonance as long as it's electrons, but if you have a lone pair like this, that's a place that I always like to start. So I'm going to take these lone pair of electrons, I'm going to lay them down between 1 and 5, and then that means I have to break this 4 to 5 double bond. So I'm going to sit those up on carbon 4. So now I'm going to change the position of these double bonds slightly so there's a new double bond between 1 and 5. Try not a little sloppy so you can still read the number 5 there. And then the double bond between 2 and 3 is still where we left it, but now that negative charge and lone pair has gone to sit on carbon number 4. So that's one resonance structure that we can draw. What about if we keep going? Let's just kind of move this charge right around the ring, shall we? If we take this charge and lay it down between 3 and 4, then we have to break the 2 to 3 double bond, set that there. And then if we bring in our pre-numbered structure, we can fill in the double bonds. We now made one between 3 and 4, but that one between 1 and 5 is still there. Now carbon 2 has the negative charge on it. We're not done. Let's keep going. If we take that charge, and again, we're going to keep going the same direction around the ring. Let it come down here between 2 and 1, and then we'll break this 1 to 5 bond, set those on carbon 5. We'll arrive at this position, where now we made a 2 to 1 double bond, but that 3 to 4 double bond is still there. And that negative charge can sit on carbon number 5. What happens if we keep going? Now lay that down between 4 and 5, break this 3 to 4 bond and sit those on number 3. Bring in our pre-numbered structure. And then we have a 4 to 5 double bond, and 3 has the lone pair negative charge, and 2 to 1 still has a double bond. So at this point, you may be really tired of drawing resonance forms, and you'll not be happy when you hear me say, let's keep going. If we keep going in the same direction, right, lay these down between 2 and 3 and put these onto 1, guess where that gets us? Right back to the start, because we started with the negative charge on 1 and having a 2, 3, and 4, 5 double bond. So this set of resonance forms shows you how, even though this ring maybe looks kind of funny, and even the resonance is a little bit choppy and jumpy, where the negative charge kind of goes on every other carbon, it can still sit on every single carbon in this ring. It sits on 1 in this form, it sits on 2 in this form, it sits on 3 in the final form, it sits on 4 here, and it sits on 5 here. So that charge is evenly spread around the whole ring by resonance. So that's how resonance plays into the sort of the defining characteristics of aromaticity. Resonance is also important when we talk about what groups are on our benzene rings, because benzene is fine, and we're definitely going to do some reactions with plain old benzene, but they're kind of boring. No offense, benzene, you're cool, but it's a little simple. Sometimes we like to add some other extra groups on there that are a little bit more fun and interesting. So this is a molecule, we saw this in the first lecture of the unit. This is phenol, which is an alcohol that happens to be attached to a benzene ring. So we would call this an aromatic alcohol. If we think about resonance here, that's going to have an effect on what we're coming up to in the next lecture. That's why I want to start thinking about it a little bit now, so that we can practice our resonance and look ahead to what's coming next. So if we think about our benzene ring here, we've got those double bonds that we can resonate around in a circle, just like this. I'm going to draw the arrows in. We can resonate like that, and that's great. This is what myself and some other chemists will call a cowardly resonance form, because it's not really interesting. It's important historically to chemistry, the fact that we are allowed to do this, but it doesn't change anything about the molecule. It doesn't tell us anything about the reactivity of this benzene ring or this phenol. So what other resonance can we do here? Well, we have this oxygen atom that to me is just screaming out, hey, I've got lone pair of electrons here. What would happen if we use those to do some resonance? So let's look for our motif here of resonance. If we have a pair of electrons here, we gotta always start with electrons. They have to be right on a single bond, and that single bond has to be attached to a double bond. So we do have the right motif here in order to be able to resonate. So let's try that. Let's draw what we would start with here. We're gonna bring those electrons down onto that single bond to form a new double bond. And then we're gonna have to break this double bond here, and we'll set that charge right over there. Draw our little resonance arrow here. So we made a new double bond between the C and the O. That H is still there. But now that oxygen is not so happy, right? It doesn't like to have 3 bonds, so it becomes positively charged. This alkene on the side is not changed, and the one kind of toward the bottom is not changed, but we broke this one that was here. So now those 2 electrons, right, in that bond are kind of sitting here outside the ring, sort of, on top of it, that you don't have to worry about in space where these are. But now we have this lone pair of electrons that's kind of in a weird spot on the ring, like some of the examples we looked at in the deciding whether things were aromatic, antiaromatic, or non-aromatic slide. So we can walk this around the ring much like we did for the last example. So let's just bring this down and over to here, break that pi bond. That one on the side stays the same. And we made a new one on this side of the ring. Everything with our OH has stayed the same. But now that charge is sitting at the bottom of the ring. Let's keep going. We're going to bring this around here, break this bond, and set those up there. We get to that resonance form. And you're already going to be hearing it in your sleep. Let's keep going. Let's resonate some more. We'll bring those ones down, and then we'll actually go ahead and push all the way up to that oxygen, right? Because that's the motif we need in order to resonate. And what that does is it'll get us right back to where we started, which is kind of nice. So I'll draw, this is a duplicate copy of that first structure, but I'll draw it down here at the end, like so. Well, now it's not exactly a duplicate, actually, right? Because the position of the double bonds inside of the ring has changed. And we didn't do it in a cowardly way. We did it in a very, very rigorous intellectual way, where we used the lone pair of electrons on that oxygen to kind of put them inside of the ring, walk that charge around, and then it ended up in the same place, just with a different arrangement of those pi bonds in the benzene ring. So this is a nice resonance form series that explains the reactivity of this compound called phenol, right? And we're not going to draw it out right now, but think about the resonance hybrid for this, if you were to draw one. In fact, that's good practice. If you'd like to pause the video now and draw the resonance hybrid, we'll talk about those in the next lecture. But think about what you would need to draw, right? We know that the bonds are going to go all the way around the ring, but the last step we do in drawing a resonance hybrid is to think about where these partial charges are sitting. They kind of sit at the very bottom of the ring, and then on either side directly adjacent to that OH group. So that's kind of an interesting pattern. We'll see why that pattern is important of where those charges are in the next lecture. Let's look at another example of a benzene derivative, right? This is a related compound to benzene. This is nitrobenzene because it has an NO2 or a nitro group on it. And we can do the same thing here. We can draw some resonance. So let's get started. First things first, we have to find our motif because, I don't know, maybe it's a little tougher to see on this one, but we don't have an oxygen directly bonded to the ring, so we can't do the same type of motif. We have these oxygens out here. They're kind of far away. We can't use this nitrogen to put any electrons in either because it has no lone pairs available to it. It's positively charged. It's kind of unhappy. So if we think about what our motifs are, again, we can do our cowardly resonance form inside the benzene ring, but that's no fun. We want to do something a little more interesting than that. What if we take our pi bonding electrons like we did in some of the examples in the previous lecture? If we take those and then want to do something with this group, we have a set of electrons there, we have a single bond here, and then we have a double bond there. So we could kind of go the other way, sort of outside of the ring, with the pair of electrons that are already in the benzene ring and in bonding capacity. So this one, again, like I said, maybe a little bit tougher of a motif to see, especially because this nitrogen here is in the middle distracting, but we're allowed to resonate over a nitrogen, no problem. So let's take these electrons here. In fact, I'll leave those drawn in like so, and then we'll bring them out of the ring to form a new CN double bond, and we'll break this NO bond. That'll give us a resonance form that looks like this, where now we made that new CN bond, as I already said. Now these oxygens have negative charges on them, right? One of them is always going to, based on the identity of the nitro group, but we have to check our charge balance here. We had a negative charge and a positive charge to start with, which means overall neutral. And then we have a negative charge and a positive charge. Those cancel out, but we made a new negative charge here. So we need another positive charge to balance that out. Also, if you're looking at this carbon and thinking that looks a little bit lonely and sad right now, well, it is because you just took electrons away from it. And so it has to have a positive charge. Okay, and so now maybe this looks a little bit more familiar to us from some of the examples in the previous lecture of having an empty p orbital positive charge and an adjacent alkene, right, that we're allowed to resonate into. So we can take these electrons, let them fall down there on that sort of side of the ring, and that'll get us a resonance form that looks like this. For the sake of time, I'm not going to bother drawing in all of the lone pairs on those oxygens. And then when we move these electrons, that positive charge has changed positions and ended up at the bottom part of the ring. Note that I don't say we moved it because you are not allowed to move positive charges. I don't want to see that in this unit, please and thank you. What we're moving instead is the electrons. So let's move the electrons in this bond here on this side of the ring, pull those down like so. And then we'll get to this resonance form with the positive charge now at that top side of the ring. And then last but not least, if we want to kind of get back to sort of like where we started, what we can do is use some of the electrons from our oxygens. So there's electrons, single bond, double bond, and then here's a single bond that has that p orbital in it. So we're allowed to resonate down to there as well. That's a little bit of an extended version of our motif, but we're definitely allowed to do it. So we can bring these electrons down like so, and then kind of just scoot these ones over like that to help fill in that positive charge, that vacant p orbital. And then we get to here. We made a new NO double bond. One of them is still negatively charged. And now we've sort of restored the aromaticity to that ring. It's nice, but now the bonds are kind of gone in a different way around the ring and not in a cowardly resonance form kind of a way. Here, we had to actually pull some electrons out of the ring, right? They hung out on that nitro group, and then we resonated a positive charge around the ring by moving our electrons. So if you look at what happened here, I think you'll find that it's no coincidence where those positive charges ended up. They ended up here at this side, here at this side, and down at the bottom of the ring. So that's interesting. Even though it was a totally opposite charge, the structure of benzene made it so that the charges ended up at the same place. But the fact that they are opposite sign charges, positive and negative, is going to have different implications for their reactivity. So think about these resonance forms. I may have you practice drawing some more of them coming up on your homework to start to think about what's coming up next. So there is a little bit to review and practice, but I'm so excited to get to the next bit of this unit where we're going to talk about substitution reactions on benzene. And they're going to be very different from our SN1, SN2 substitution reactions. So I'm getting ahead of myself, telling you to look ahead. Here are some things to review and practice before we move on. Really hammer home, practice identifying which molecules are aromatic, antiaromatic, and non-aromatic. Like I said, this will definitely be on homework and it will definitely be on the exam. So you want to be careful with that and practice using those 3 rules. If you go through them in order, whatever order you like, then you'll have a good process in place and you'll be able to run through those identifying practice problems and on the exam really quickly. Then we also want to practice drawing some resonance structures of either the aromatic rings, like we did with that 5-membered ring where we drew 5 resonance forms, showing how that negative charge went all the way around the ring. And we practiced with some of those substituted benzenes, or the benzenes that have other functional groups attached to the outside. So practice, practice, practice these resonance form drawings, especially when it comes to aromatic rings. Like we said in the previous lecture, I'm not going to ask you to draw too many resonance hybrids or pick major forms, but we do want to be aware of those concepts and able to apply them to these cool aromatic molecules in order to do, like I said, what we're going to do next, substitution on benzene. If you have any questions about the concept of aromaticity or how to draw resonance forms or what resonance really is, feel free to just ask. You can send me an email or a Canvas message. You can post in the discussion forum, or you can stop by office hours. Tuesdays, and Wednesdays. Check the syllabus for times or email me if you're not sure when those office hours are. Hope you're hanging in there through the end of the semester. We're almost there, y'all. Stay safe and stay sane. And until next time, take care.